Alright, welcome back. So now I want to sketch through looking at what happens when we put an object in front of a concave mirror. So we can think about it. There's a number of places that we can put an object. So what we do is we break it down into multiple regions. So we have region 1. So region 1 is the point past the center point. So remember, the center point is the center of the spherical mirror. So this corresponds to the radius of the spherical mirror. So if we're past that, that's called region 1. If we move past the center point, then we go to region 2, where we are in between the focal point and the center point. Then if we move from region 2 past the focal point, then we move into what we call region 3. Region 3 is in between the focal point and the mirror. As far as I know, this description is something that only we use, but it seems sort of convenient when you do this. So if you try and Google this or something, if you say, what's a region 1 with a concave mirror, I'm not sure you'll come up with anything useful, but hopefully this is clear enough. It's not going to give you too much trouble. So to start with, we want to know what happens when we have a concave mirror and we have an object at infinity. So that means our object is very far away, and so the rays coming from it are all parallel to each other. And so what happens is what you'd expect. So when you have parallel rays, they hit the concave mirror, and then they focus onto the focal point. So if we want to find the distance of the image, we would use the mirror equation. So 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal point. So the distance to the object is infinity. So that's 1 over infinity plus 1 over di is equal to 1 over f. So 1 divided by infinity, that's just 0. So that means 1 over di is equal to 1 over f, or in this case, so the distance to the image is at the focal point, right? So remember, this is only when your object's at infinity. We're kind of walking through these different possibilities. If we want to know the magnification is the negative of the distance to the image divided by the distance to the object. So the distance to the image is the negative of the focal point. The distance to the object is infinity, so that means that's 0. So our magnification here is just 0. So that's kind of how you solve these problems. You look at your mirror image, and then you figure out your distance of your object, you find your focal point, and then you solve for the distance of the image. Then you kind of look at the ray tracing to do kind of a sanity check. So our next example is when we're in region 1. So that means we are between the center point and, well, we're beyond the center point. So our object is placed 30 centimeters from the concave mirror, and our focal length is 10 centimeters. So focal length is 10 centimeters, center point is 20 centimeters, so that confirms at 30 centimeters we are past the center point. If we do our ray tracing, if we look at this, it looks like our image is smaller than the object, and it looks like it's inverted. And if we want to do a sanity check, we've only drawn 2 of the lines here. We did the P ray and the F ray. So if we want to do the C ray goes through here, and so it confirms it goes through the image point. So to solve for the distance to the image, we use our mirror equation. So 1 over dO plus 1 over di is equal to 1 over f. Thanks. So, all right, let's do that again. 1 over dO plus 1 over di is equal to 1 over f. So that means distance to our object is 1 over 30. Distance is what we're trying to find. Focal length is 10 centimeters. So that means if we want to solve this, so if we're going to do the algebra here, this becomes 1 over 30 plus 1 over di is equal to 3 over 30. So you kind of see what I'm doing here. So I multiplied both top and bottom by 3. And so that means 1 over di is equal to 3 over 30 minus 1 over 30. So that means 1 over di is equal to 2 over 30. And di is equal to 15 centimeters. So that's the algebra to do here. I probably won't do that every time. But the point is, that puts us the distance of the image in between the focal point and the center point, so that checks out, and that gives us a proper distance. So I haven't left myself a lot of room here, but if I want to do the magnification, so that is the negative of the distance of the image divided by the distance to the object. So that is equal to negative distance of the image is 15, distance to the object is 30, so that means the magnification is negative 0.5. So the fact that it's negative tells us it's inverted, and the fact that its magnitude is 0.5 tells us that the image has half the height as the original object. So the fact that it's negative, it means it's upside down. It doesn't mean that it's smaller. So that checks out. Our image is inverted in our ray tracing, so it looks like we've solved this problem correctly. All right, let's keep going through here. So now we have put our object at the center point. So our object is 20 centimeters, focal length is 10 centimeters, center point is twice the focal length, so 20 centimeters checks out. So to do this one, we do what we just did. We write down our mirror equation, 1 over the distance to the object plus 1 over distance to the image is equal to 1 over the focal length. So this becomes 1 over 20 plus 1 over di is equal to 1 over 10. So this one, hopefully you can see this, but if you work this out, this is 1 over di is equal to 1 over 10 minus 1 over 20, and that distance to the image is going to be 20 centimeters. So that means that the position of the object and the image are exactly the same. They're both at 20 centimeters. But this only happens when you put your object at the C point on the mirror. If we want to know the magnification, so this is the negative of the distance of the image divided by the distance to the object. So the distance to the image is 20, and it's negative, so that's going to be negative 20 divided by 20. So our magnification is negative 1. So that means the image is the same size as the object, but it's inverted, so it's upside down. And that's what we see in our ray tracing, so that also checks out. So we keep moving our object in here. So now we've moved our object in between the focal point and the center point. So 1 over di plus 1 over do is equal to 1 over f. Yes, I flipped that there, but that means that in this case our focal length is 20 and our object is 30, so the center point is going to be twice the focal length, so that's going to be 40. So this confirms that we really are in region 2 in between the center point and the focal point. So 1 over di is equal to 1 over, plus 1 over 30 is equal to 1 over the focal point. And so that then means 1 over di plus 1 over 30 is equal to 1 over 20. So if we do our math on this, this becomes 3/60 minus 2/60 gives us 1 over 60. So the distance to the image is 60 centimeters. So you can probably use your calculator for this one. So 1 divided by 20 minus 1 divided by 30 is equal to 1 divided by the distance to the image. So if we do that, then we might want to find the magnification. So this is negative 1 over di divided by do. So distance to the image is 60. Distance to the object is 30. So our magnification is negative 2. This checks out. We look at our ray trace here. It's inverted, so it's negative, and also it's larger than the object, so that the magnification should have a magnitude greater than 1. Okay, I guess we keep moving. So now we put our object at the focal point. So here, the focal length is 10 centimeters. The object is at 10 centimeters. So this creates a bit of an issue here, right? So if we do our mirror formula, 1 over di plus 1 over do is equal to 1 over the focal point. So focal length is 1 over 10, and the distance to the object is 10. So that means if we subtract 1 over 10 from each side, 1 over di is equal to 0. So what does that mean? That means that the distance to the image is equal to infinity. right? So 1 divided by infinity is 0. So that means that the basically that the image never forms. That if you try and put an object at the focal length, then you're not going to be able to see any image at all. So I'm going to try this real quick. Let's do a demo. Let's see how well this works. So I've got a better pen here. So I've got an object, and I am going to, it's hidden by the light here, but I'm going to, I'm holding the pen above the mirror here. So it's more of a parabolic than a true spherical mirror. But if I move it closer and closer to the focal point, oops, that's the real thing. So watch into the, and here we've just started to hit the focal point. So what happens as we move it through the focal point, basically the whole thing just kind of blows up. The light rays just all run parallel to each other, and so there's effectively no real image forming. So you just kind of get this funny sort of blob-looking thing. Notice if we're closer, the reflection is the same direction as the pen. If I move the other way, now the reflection's going the opposite way. So we can see something funny happens when we move through the focal point. All right, and so I guess if we're doing magnification, so what we do with magnification, this would be negative di divided by do. So this is negative infinity divided by 10. So the magnification is negative infinity, or infinity. No, it's kind of undetermined thing here. All right, and so last here, we finally move our object inside of region 3. So here, our object is at 10 centimeters, while our focal length is 20. So to solve this one, 1 over di plus 1 over do is equal to 1 over the focal length. So that means 1 over di plus 1 over 20 is equal to 1. Oops, the object is 10, my bad. The object is 10, and the focal length is 20. So that means that to do this, this becomes 1 over di is equal to 1 over 20 minus 2 over 20, which is equal to negative 1 over 20. So notice, what's happening here is once we move into region 3, the distance to the image becomes negative, right? So we saw on the mirror that the image went from being inverted from when you're further away, and it became the same direction when we moved through the focal point. So that's what's happening there. So that means the image is now located on the opposite side of the mirror as the object, because that di is negative. So if we want to know magnification, this is negative di over do. So distance to the image is negative 20, and distance to the object is 10. And notice there's an extra negative here, so now the magnification here should be 2. So notice it is magnified, so when we're inside of the focal point, the mirror does magnify the object. Alright, so I did that kind of fast, but that's sort of how you do these problems. Basically, you use the mirror equation, and then using that, you solve the position of the image, and once you know that, you can find the magnification. Alright, so you have some of these to do, so good luck with that.